In this video, we are going to see residue of an analytic function f of z at the point z is equal to a. So let us see how to calculate residue of f of z, or else okay, if z equal to a is an isolated singular point or singularity of the function f of z, we can find the Laurent series. That is f of z is equal to summation over n is equal to 0 to infinity a n z minus a raised to the power n plus summation over n is equal to 1 to infinity b n divided by z minus a raised to the power n. So we can find a solution for this Laurent series at the point z is equal to a. The coefficient b1 of 1 upon z minus a in Laurent series of the function f of z is called the residue of f of z at the point z is equal to a. But we know that by Laurent series theorem, b1 is equal to 1 upon 2 pi I integration over c f of z into dz. The first case, if z equal to a is a simple pole of f of z, then the function f of z is equal to summation over n is equal to 0 to infinity a n z minus a raised to the power n plus b1 divided by z minus a. That means z equal to a is a simple pole. That means the order is 1. So we are omitting the remaining one. Multiply z minus a on both the sides. So z minus a into f of z is equal to summation over n is equal to 0 to infinity a n z minus a power n into z minus a is z minus a power n plus 1 plus b1. Now taking a limit as z approaches to a on this equation, z minus a into f of z is equal to, when we take limit as z tends to a minus a is 0, 0 into anything is 0. So 0 plus b1. So b1 is the residue of this function at the point z is equal to a. So residue of f of z at the point z equal to a is limit as z approaches to a, z minus a into f of z. So case 2, if z equal to a, if z equal to a is a pole of order m, then the residue of f of z at the point z equal to a is 1 by m minus 1 factorial limit as z approaches to a, differentiate the function, differentiate z minus a into f of z with respect to z m minus 1 times. So this is the calculation if z equal to a is a pole of order m. The proof of this formula is similar to the first case. So let us solve a problem, some example problem. Let us see. The first question is, classify the singularity of z plus 2 divided by z minus 2 into z plus 1 the whole square, and also find the residue of each point or each singularity, each singular point. Solution: So to find the singularity, the step 1 is equating denominator to 0 of the given function. So here the denominator is z minus 2 into z plus 1 raised to the power 2 is equal to 0. Therefore z minus 2 equal to 0, z plus 1 raised to the power is equal to 0. So z equal to 2 and z is equal to minus 1. Z equal to 2 is a simple pole. As we studied in the previous video lecture, we have seen the definition of pole, essential singularity and removable singularity, isolated singularity, 0,7 analytic function. You can refer that video to find the pole. Simple pole, z equal to 2 is a simple pole. The reason is the order is 1 and z equal to minus 1 is a pole of order 2. So that's all the first question, and the second one is also find the residue of each singular point. So we have to find the residue of each singular point. So residue of f of z at the point z equal to 2 is, since z equal to 2 is a simple pole, so just take a limit as z approaches to 2, then z minus 2 into f of z. So which is equal to a limit as z approaches to 2, z minus 2 into z plus 2 the whole divided by z minus 2 into z plus 1 raised to the power 2. This and this get cancelled. Now substitute the limit z equal to 2, then 2 plus 2 is 4 upon 2 plus 1 is 3, 3 square is 9. So the residue of f of z at the point z equal to 2 is 4 by 9. Next we have to calculate the residue of the function f of z at the point z is equal to minus 1. So already we see that z equal to minus 1 is not a simple pole, it is a pole of order 2. Therefore we have to differentiate one time. So 1 by 1 factorial limit as z approaches to minus 1 d by dz of z plus 1 into f of z. 1 by 1 factorial is 1. So in the next step, limit as z approaches to minus 1 d by dz z plus 1 into f of z is z plus 2 upon z minus 2 into z plus 1 the whole square, z plus 1 the whole square, z plus 1 the whole square get cancelled. Now we have to differentiate the remaining part after cancelling the terms. So it is u by v method. V into differentiation of the numerator is 1 minus numerator into differentiation of the denominator is 1 upon denominator the whole square. So we substitute z equal to minus 1 in this function. So minus 1 minus 2 into 1 is minus 3. So minus of, we put z equal to minus 1 plus 2 upon minus 1 minus 2 raised to the power 2, which is equal to minus 3. Minus 1 plus 2 is 1, minus 1 again upon minus 1 minus 2 is minus 3, minus 3 raised to the power 2 is 9. So minus 4 upon 9. This is residue of f of z at the point z is equal to minus 1. So we'll see the Cauchy's residue theorem. The statement of the Cauchy residue theorem is, if f of z is analytic at all points inside and on C, inside and on the simple closed curve C, except at finite number of isolated finite number of isolated singularities say z1, z2, etc., zn, then integration over C f of z into dz is equal to 2 pi I into sum of the residues of f of z at the points z1, z2, etc., zn. So let us solve a problem based on Cauchy residue theorem. So let us consider the first problem, the first example, the function. Let us consider the first function. Evaluate integration over C z plus 2 upon z minus 2 into z plus 1 raised to the power 2 into dz, where C such that modulus of z is less than or equal to 3 by 2, that is 1.5, using Cauchy residue theorem. Solution. The first step is equating the denominators to 0. So we get z equal to 2 and z is equal to minus 1. So we have to check whether which of these points or lies inside or lies outside the circle modulus of z is less than or equal to 3 by 2, that is 1.5. So it is easy to check whether this point z equal to 2 is less than the radius 1.5, then it is lies inside, or otherwise it is lies outside. Z equal to 2, so modulus of 2 is equal to 2, 2 is greater than 1.5, therefore z equal to 2 lies outside C, such that modulus of z less than or equal to 1.5. And the point z equal to minus 1, modulus of minus 1 is plus 1, which is less than 1.5, therefore z equal to minus 1 lies inside C. Let us see such that modulus of z less than or equal to 1.5. So now we have to calculate the residue of f of z at the point z is equal to minus 1, but we no need to find the residue of the function f of z at the point z equal to 2. Since the reason is inside the circle z equal to 2, we are getting some value for z equal to 2. So z equal to minus 1, okay, z equal to minus 1 is a pole. The point z equal to minus 1 is a pole of order 2. Therefore residue of f of z at the point z equal to minus 1 is limit over z approaches to minus 1 by 1 factorial d by dz z plus 1 the whole square into f of z. Just now we found residue for the same function, therefore the answer is minus 4 by 9 by Cauchy's residue theorem. Integration over C z plus 2 upon z minus 2 into z plus 1 raised to the power 2 into 2 dz is 2 pi I into sum of the residues of f of z. This is the statement of the theorem. So 2 pi I into, we have only one residue of f of z, that nothing but minus 4 by 9. It is equal to minus 8 upon 9 into pi I. That's all the answer. Let us calculate one more problem. Let us solve another problem using Cauchy residue theorem. Example 2. Evaluate integration over C dz upon z square plus 4 raised to the power 2, where the simple closed curve C such that modulus of z minus I is equal to 2. Solution. So we have denominator, therefore z square plus 4 raised to the power 2 is equal to 0. This is the first step. Next step is z square plus 4 is equal to 0, z square is equal to minus 4, z is equal to plus or minus 2i. In the next step, we have to check the point z equal to 2i and z equal to minus 2i lies inside or outside the circle modulus of z minus I is equal to 2. So substitute z equal to 2i in the given curve. 2i minus I is equal to modulus of I, the value is 1, 1 is less than the radius 2. Therefore, z equal to 2i lies inside C. I is equal to 2. And the point z equal to minus 2i and minus I is equal to modulus of minus 3i is equal to 3, which is greater than the radius 2. Therefore, z equal to minus 2i lies outside the circle or outside the simple closed curve C, such that modulus of z minus I is equal to 2. Therefore, we have to find the residue of the function f of z. It is nothing but 1 upon z square plus 4 raised to the power 4 at the point z is equal to 2i alone. So, but z equal to 2i is a pole of order 2. Therefore, 1 by 1 factorial into limit over z approaches to 2i d by dz into z minus 2i the whole square into f of z, which is equal to limit z approaches to 2i d by dz z minus 2i the whole square 1 upon z square plus 4 the whole square can be written as z plus 2i into z minus 2i the whole square. Now we can cancel, that is ab the whole square, therefore a square b square. So we can cancel this term. So limit, in next step we have limit over z approaches to 2i d divided by dz z minus 2i the whole square into 1 upon z plus 2i the whole square into z minus 2i the whole square. Therefore, the common terms get cancelled. We have remaining this term. So, we have to differentiate this term with respect to z. So, limit z approaches to 2i. So, the answer is minus 2 divided by z plus 2i the whole cube. Now, when we take the limit, minus 2 divided by 2i plus 2i is 4i the whole cube minus 2 divided by 4i the whole cube, that is 4 cube into I cube equal to minus 2 divided by 64. I cube is minus 1, so minus into minus plus divided by I, 64i. So by Cauchy's residue theorem, we have integral over C dz upon z square plus 4 raised to the power 2 is 2 pi I into sum of the residues. So the residue is 2 divided by minus 2 divided by 4 cube is 64. So this is plus I. So 4 pi I divided by 64i, I and get cancelled, 4 and 64 get cancelled by 16. Therefore, the answer is pi upon 16. This is the answer for the given function. Verse C. That's all. Thank you.